If the stars and gas are disappearing in a certain location, it could indicate the presence of a black hole in that area. If we were to see a black hole, it would mean that we are already being pulled inside, along with all the celestial objects in our galaxy, including the Sun, the Moon, and all the planets. Hello, I am Victor. Today we're going to talk about what is gravity and how it affects the universe. Gravity is a fundamental force that exists in the universe and is responsible for the attraction between objects with mass. It is a force that affects our daily lives in countless ways, from the way we walk on the ground to the orbit of the moon around the Earth and the grand movements of the universe at large. The discovery of gravity has a rich history that spans centuries. The ancient Greeks were the first to theorize about the nature of gravity, but it wasn't until the 17th century, thanks to the apple that landed on Sir Isaac Newton's head and helped him formulated his laws of motion and gravitation. His laws explained the motion of objects on Earth and in space, and they served as the foundation for our understanding of gravity for centuries to come. Despite the success of Newton's laws, they had limitations. They could not explain certain phenomena, such as the orbit of Mercury around the Sun, and they did not account for the warping of space-time. It wasn't until the early 20th century that Albert Einstein developed his theory of general relativity, which revolutionized our understanding of gravity. Einstein's theory is that gravity is not a force between objects, but rather a curvature of spacetime caused by the presence of mass and energy. This means that objects in free fall are actually following straight paths through curved spacetime, rather than being pulled by a force. This concept has profound implications for our understanding of the nature of gravity and the behavior of objects in the universe. One of the key differences between Newton's theory and Einstein's theory is that while Newton's theory was based on the concept of instantaneous action at a distance, where the force of gravity is transmitted instantaneously across space, Einstein's theory posits that gravity travels at the speed of light, as a wave-like disturbance in the curvature of spacetime. Another important aspect of Einstein's theory is that it predicts that the path of light is also affected by gravity, a phenomenon known as gravitational lensing. This has been observed and confirmed through various astronomical observations, such as the bending of light around massive objects like galaxies. Einstein's theory also predicted the existence of gravitational waves, which are ripples in the fabric of spacetime that propagate through the universe at the speed of light. These waves were detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, providing direct evidence for the existence of gravitational waves and confirming another aspect of Einstein's theory. The Laser Interferometer Gravitational Wave Observatory, LIGO, is a special place where scientists study waves that travel through space and time called gravitational waves. These waves happen when really big things like black holes or neutron stars crash into each other. What is a neutron star? Neutron stars are incredibly dense and tiny objects in space that are formed from the remnants of a massive star that has exploded in a supernova. They are so dense that a single teaspoon of their material would weigh as much as a mountain on Earth. This is because all of the protons and electrons in their atoms have been squeezed together to form neutrons, hence their name. Neutron stars, with their strong magnetic fields, intense radiation, and extreme conditions, are fascinating objects for astronomers to study in order to gain insights into the behavior of matter during supernova explosions. LIGO uses two very long, L-shaped detectors called interferometers to detect gravitational waves. These detectors are located in two different states in the United States, Washington and Louisiana. Each interferometer is made up of two long tubes, which are about 4 kilometers long and arranged in the shape of an L. Gravitational waves cause tiny distortions in spacetime that change the length of the L-shaped tubes by a very small amount, much less than the width of a proton. By measuring these changes, LIGO can detect and study gravitational waves. The interferometers use lasers to measure the changes in length, which are caused by the passing of a gravitational wave, and convert the measurements into data that scientists can analyze. LIGO was constructed over a period of several years, with the first observatory in Hanford, Washington starting construction in 1994 and the second observatory in Livingston, Louisiana starting construction in 1995. The two observatories were completed in 2002 and underwent several upgrades and improvements in subsequent years to increase their sensitivity. The first direct detection of gravitational waves was made by LIGO on September 14, 2015, which was a major breakthrough in physics and astronomy. The discovery was announced on February 11, 2016, and was the result of the merger of two black holes, which caused ripples in spacetime that were detected by the LIGO detectors. Since then, LIGO has detected several other gravitational wave events, including the merger of two neutron stars on August 17, 2017, and multiple black hole mergers. As of September 2021, LIGO has detected a total of 50 gravitational wave events. This means there are a lot of activities out there in the universe. Black holes can range in size from a few times the mass of the Sun to billions of times the mass of the Sun. Stellar black holes, which are formed from the collapse of a single massive star, typically have a mass of between 5 and 10 times that of the Sun. Intermediate black holes, which are much rarer, have masses ranging from 100 to 100,000 times that of the Sun. Supermassive black holes, which are found at the centers of galaxies, can have masses of millions or even billions of times that of the Sun. Black holes cannot be seen directly because they do not emit detectable light or electromagnetic radiation, but their presence can be detected by observing their effects on surrounding matter such as stars and gas. If the stars and gas are disappearing in a certain location, it could indicate the presence of a black hole in that area. If we were to see a black hole, it would mean that we are already being pulled inside, along with all the celestial objects in our galaxy, including the Sun, the Moon, and all the planets. The gravity in black holes is extremely strong, and it increases as you get closer to the center or singularity of the black hole. The strength of gravity is described by the curvature of space-time, which is determined by the mass and density of the black hole. At the event horizon, the boundary beyond which nothing can escape, the gravity is so strong that not even light can escape, which is why black holes are invisible to telescopes. The gravity inside a black hole is so strong that it warps spacetime to the point where time and space become indistinguishable. This creates a strange effect where objects get stretched out like spaghetti, and hence it's called spaghettification. They are the result of the collapse of massive stars and are some of the most mysterious objects in the universe. Black holes are thought to exist for an extremely long time, with some theories suggesting that they could last for trillions of years. However, over time, black holes can lose mass and energy through a process called Hawking radiation, named after physicist Stephen Hawking, who first proposed its existence. This process is extremely slow and is only significant for very small black holes. It is currently believed that supermassive black holes, which are found in the centers of galaxies, will not completely evaporate through Hawking radiation within the age of the universe. The study of black holes has led to many important discoveries and has challenged our understanding of the laws of physics. Other interesting theories related to gravity include the concept of wormholes, which are hypothetical shortcuts through space-time, and the idea of dark matter, which is thought to make up a large portion of the universe but cannot be directly observed. There is interesting hypothesis is that dark matter may be made up of black holes that formed in the early universe, known as primordial black holes. Dark matter remains a greater mystery compared to black holes and requires further study to unravel its secrets. Gravity is a fundamental force that affects everything on Earth and in the universe. It is responsible for the attraction between all objects with mass, including planets, stars, and galaxies. Without gravity, everything would float away into space, and the dynamic structure of the universe would be drastically different. On Earth, the gravitational pull keeps everything on the surface of the planet, including the atmosphere, oceans, and all living beings. The gravitational pull of the Sun keeps the planets in their orbits, and the Moon's gravity affects the tides and helps stabilize the Earth's rotation. Gravity also plays a key role in the large-scale structure of the universe. While gravity tends to pull matter together, the universe is actually expanding at an accelerating rate due to the influence of dark energy, a mysterious force that counteracts the pull of gravity. However, over time, gravity will eventually slow down the expansion of the universe and potentially lead to a collapse in a hypothetical event known as the Big Crunch. The Big Crunch is a hypothetical scenario in the universe's ultimate fate, in which the expansion of the universe, driven by dark energy, is eventually overcome by the gravitational attraction of all matter in the universe. This would cause the universe to begin contracting and eventually collapse into a singularity, much like the Big Bang that started the universe's expansion. The concept of the Big Crunch is based on the assumption that the universe will continue to behave as it currently does and that dark energy will not counteract the gravitational pull of all matter in the universe. However, recent observations suggest that the universe's expansion may be accelerating rather than slowing down, making the occurrence of a Big Crunch less likely. Overall, gravity is a force that governs the behavior of matter in the universe, and its effects are evident on all scales, from the tiniest particles to the largest structures in the cosmos. There are some mysterious places in the world where gravity seems to behave strangely, appearing to disappear or even reverse direction. In these places, objects or people may appear to be defying gravity by remaining suspended in midair or by rolling uphill instead of downhill. These phenomena are often attributed to optical illusions caused by the layout of the surrounding landscape, which can make it difficult to accurately perceive the direction of gravity. However, the exact causes of these mysterious gravitational anomalies are still not fully understood and continue to intrigue scientists and visitors alike. There's a rumor that anti-gravity can allow to control gravity, make things fly or levitate without any engines or wings. Some people think the government is keeping secret experiments related to anti-gravity technology, but there's no real proof of it. Scientists have some ideas about how it could work, like using strange materials or energy, but they haven't been able to prove them yet. I believe that it is unlikely we will have the ability to control gravity anytime soon. However, if we do develop this technology, it could be revolutionary for humanity, leading to a new era of space exploration and potentially even colonization. It could allow us to overcome the limitations of space travel and make interstellar travel possible, opening up new possibilities for the future of humanity. Thanks for watching. Leave a comment below about your thoughts.